Good morning to you, students. Now, today we are going to see about the three topics we are going to learn. One is the Bragg equation. One is the density calculation. And one is the packing of crystals. These three topics which we are going to see now. Okay, Bragg's equation. So W.H. Bragg got a Nobel Prize to analyze the X-ray studies. The X-ray study is a best method to study the crystal, or you want to study crystal perfectly, you need to use the X-ray. The Bragg used that only. Finally, he got an equation that 2d sin theta, that is equal to n. Okay. Let me explain what is the Bragg's equation. Bragg's equation gives us the relationship between the d, theta, n and lambda. What is called d? D is interplanar distance. Interplanar distance. D is an interplanar distance in a crystal in itself. Theta, angle of refraction. Angle of the N is order of reflection. Order of reflection. Lambda is wavelength of the ray. Bragg's giving the interrelationship between the distance, interplanar distance, and the theta, angle of diffraction, and the order of reflection n and lambda wavelength. Okay. By using this formula, 2d sin theta equal to n lambda, you can get anything else. See, what are the variables here? D, interplanar distance, theta, and the n and the lambda. You have 4 betas. Okay. Now we can alter this 4. You can get the 4 data. For example, you want a d value, interplanar distance you want to know. What is the Bragg's equation? 2d sin theta, that is equal to n lambda. Now you want to calculate d. Okay. Then 2d equal to n lambda by sin theta. Then d equal to n lambda by 2 sin theta. If they ask d, they must be giving that theta, n and n. These three will be given in a question. Directly or indirectly, these are available. Okay. If you substitute these data, you can get an interplanar distance d. Then you want to calculate theta. What to do? How we can alter this formula? Simply you can go 2d sin theta, that is equal to n lambda. Then now you want the theta, no? So sin theta equal to n lambda. Then n lambda by 2d. You want the theta, n lambda sine inverse of n lambda. Okay. Then, if you want n, order of reflection n, it is needed to order of reflection n you want, what to do? With the formula 2d sine theta equal to n lambda, then n equal to 2d sine theta by lambda. That is clear. Now you want to get a lambda equal to 2d sine theta by a. So why I am elaborating writing like this, you may get up problems. You will be given among the four, any of the three will be given in a question paper. Okay. Then you need to apply the formula and you can get if you want d n lambda by 2 sine theta, you want theta equal to sine inverse n lambda by 2d, or otherwise n you want 2d sine theta by lambda, or you may ask lambda 2d sine theta by n. Many problems you have in a book and you can have practice. Wherever you see, you go with the Bragg's equation, write the Bragg's equation first, and then given data, you write the given data. After that, you want what you want. Among these four, one thing will be wanted. What you want, you write the solution and substitute it, you can get the answer. Okay. Once again, I am repeating the Bragg's equation. What is the Bragg's equation? Bragg's equation giving the interrelationship between the interplanar distance d and the angle of diffraction theta, then order of reflection n and with lambda. Okay, this is a Bragg's equation. It is used to study the study of the crystal. By using this formula, you can calculate the edge length A also can be calculated. Okay. Then let us move on to the next segment, that is density calculation. Okay. Okay, let us calculate the density. Density rho can be given mass of the unit cell, divided by volume. Okay, mass of the unit cell divided by the volume. Then mass of the unit cell we need to calculate. Mass of the unit cell, that is equal to total number of atoms in unit cell into mass of one atom. So the density of the unit cell can be calculated mass of the unit cell divided by the volume of the unit cell. Okay, volume of the unit cell. Then here mass of the one unit cell, can be calculated total number of atoms in a unit cell into mass of one atom. Then mass of one atom. That is equal to molar mass of the atom by Avogadro number. Avogadro's number. Molar mass can be given as capital M. Avogadro number can be given as M. So, by using this formula, mass of one atom, molar mass, molecular mass divided by Avogadro number, that we can calculate. Then total number of atoms in a unit cell that is equal to M. N may be differ. N equal to total number of atoms in a system. It will vary. For simple cubic, N equal to 1. For a BCC, N equal to 2. For FCC, N equal to 3. That already you have studied. N equal to 4. You have studied in the previous class. Simple cubic, you have only one. Body center cubic, number of atoms present in the body center cubic, 2. The number of atoms present in the face centered cubic, 4. Okay, this contribution, let me recall you. In a simple cubic, if you take, in simple cubic, the atoms are present only at the corners. Already discussed in first classes, even though only corners. What is the contribution of corner? 1 by 8. Total corners are 8. So that is 1. That's why N equal to 1 for simple cubic. Whereas N equal to 2 for body centered cubic, in the body centered cubic, the same way in the corners, in addition to that corner, you will have an atom at the body, center of the body. So 1 by 8 into 8 plus 1. 1 plus 1 equal to 2. That is a contribution. So total number of atoms in a body centered cubic, you will have 2 atoms. Likewise, N equal to 4 for a face centered cubic. Face centered cubic, you will have 1 by 8 into 1, 8 plus, there are 6 faces. 6 faces. Space contribution is 1 by 2. So 3. 1 plus 3 equal to 4. So total number of atoms present in a face center FCC, you will have 4 atoms. So what is the type of atom is given, body centered or face centered or a simple cubic? According to that, you have to substitute the N value. Now let us go to the formula. Mass of the unit cell equal to total number of atoms in a unit cell into mass of the one atom. Now total number of atoms equal to N, mass of the one atom into M. So mass of the unit cell, now you got mass of the unit cell. Mass of the unit cell. What is the mass of the unit cell? Mass of the unit cell equal to total number of atoms in a unit cell. Total number of atoms in a unit cell, that is equal to N into mass of one atom. We have calculated, we have derived, that is a molecular mass by N. So whatever we got so far we got a mass of the unit cell. Okay, mass of the unit cell. Till we our aim is to calculate the density. Density we not yet go. But what is the density? Mass of the one unit cell by volume. So here density equal to mass of the one unit cell. What is the mass of the one unit cell? N into M by N. Okay. Then volume. Volume is equal to A cube. Volume of the unit cell is given by A cube. Okay. A is nothing but a edge line. So volume is a cube 1 by A cube. And the formula will be N into M by A cube into N. So the density rho can be calculated from N into M by A cube into N. This is the way you can get the density. Okay. Once again I am repeating how we can calculate the density. Density equal to mass of the unit cell divided by volume of the unit cell. Then mass of the one unit cell. Mass of the unit cell equal to total number of atoms present in the unit cell into mass of one atom. Then mass of one atom, that is equal to molar mass of an atom divided by Avogadro number. Molar mass can be given by capital M, Avogadro number Na. Then we need a total number of atoms in a unit cell equal to n may varying for the system, cubic system. If it is a body center simple cubic, you are having n equal to 1. Body center cubic, you have n equal to 2. Face center cubic, you have n equal to 4. So n may be vary. Regarding the concept, you can change the n value. So mass of the unit cell equal to n into m by na. Okay. Now let us move on to the density. Density is nothing but a mass of the unit cell by volume. Volume equal to A cube. A is nothing but a edge length. A is nothing but a edge length. So density equal to n into m by na by A cube. So n into m A cube by na. So rho equal to, you can have a formula like this. So what are the variables here? What are the variables here? N, rho, n, m, a. There is constant. So what is the problem you may have in your book? They asked rho first. Rho, you have a formula, direct formula, n into m by a cube by na. Okay, this is type of one problem regarding the density. As the example problem is given like this, a value will be given. If you go in a book, you can see a value is given. They will ask the density. The particular name of the element will be given. If, for example, barium is given, what is the molecular mass, molar mass of barium, you have to write. That will be given in a bracket or you have to memorize. That's it. N value, what is the system? Barium will have body center cubic mean body center cubic n equal to 2, you have to apply. Then edge length will be given. Always you see what is the answer, picometer or centimeter or nanometer, which Armstrong unit, what they are giving, what is your answer. Relevant to the answer should be given. Sometimes they will give some other unit. They will give data in picometer. They will ask answer in a centimeter. Okay. So you have to change, convert the picometer into centimeter. Then you have to do the problem. That's you have to be very keen about this. For example, considering example problem, you can see that they have given a edge length in a picometer they will give, but the question is asked in a centimeter. So just while writing the data itself, you convert the picometer into centimeter. Then you proceed your problem by using this formula. You find the answer what they asked. Okay, right? Then what are the others? Number of items already it's fixed. That will not be asked because the system is given. That question will not be asked because number of atoms, that is fixed value, that is BCC equal to 2, SC equal to 1, FCC equal to 4. So these three will be asked. Molecular mass may be asked, unknown. They will say that is unknown crystal. So molecular mass be asked. Molecular mass asked mean how we have to convert the formula. M is asked. So rho density will be given, edge length will be there, and the Avogadro number already fixed divided by n. If you do this by using this formula, you can calculate the molecular mass. Okay. Then what else? Edge length may be asked. The density is provided, density is given to you. Then molar mass already fixed. They will say the name of the element, or otherwise they will give in a bracket. So if they ask the edge length A, if they ask the edge length A, what to do? This is the formula, rho into A cube we can easily calculate. Already write again you can write A cube equal to n into m rho into n. That's all. But A cube we can calculate A. Okay. These are the various form of the density calculation problems. Why I am elaborately writing like this? The question may be asked, not only density they will ask, density may be asked first, or otherwise molecular mass of the molar mass of the crystal may be asked, or otherwise edge length may be asked. For you should be ready with for anything they asked. Okay, that's why I am elaborately writing this. Once again we can go with the density. Density is nothing but a mass of the unit cell by volume. Volume A cube, A is edge length. Mass of the unit cell is nothing but a total number of atoms in a unit cell and a mass of one atom. What is the mass of one atom? Molar mass of atom by Avogadro number. Molar mass can be capital M. Avogadro number can be given by Na. Then Total number of atoms in a unit cell equal to n. N may be vary for 3 different system. Simple cubic 1, BCC, body center cubic 2, face center cubic 4. If you apply this formula, mass of the one unit cell is equal to n into m by Na. What is the formula for density? Density mass of the unit cell divided by volume. Volume A cube, then you can find the density equal to n into capital M by A cube into Na. The unit of particular data should be provided and final unit should be derived. Okay, then let us move on to the packing in crystal. Okay, let us see in the packing of crystal. Packing in crystal. You can see in the fruit stall how the fruits are arranged in order. Okay, the same way the atoms or ions or molecules are present in a unit cell in a crystal. Okay, the same way. So if you see in a fruit stall the apples or oranges, they are arranged properly in order. That will be looking like that only. Atoms or ions or molecules are arranged in a crystal in a unit cell. That how the arrangements are there, that we are going to see now. First, linear arrangement. That is 1D. Linear arrangement are 1D. Before that, you should know the coordination number. Coordination number. What is called coordination number? Okay. Coordination number is nothing but the nearest members in a crystal lattice. Nearest member in a crystal lattice. For example, for linear arrangement, you will have a linear arrangement like this. So atoms or ions or molecules are linearly arranged in a lattice. This is called a linear arrangement or one dimensional arrangement. Here if you take any one of the atom, I am marking this atom, it is directly closely attached with two other atoms. This is a closed neighbor to this sphere. So number of sphere closely or nearly attached to that sphere is called a coordination number. This is called a coordination number. So what is the coordination number for a linear arrangement? You take any of if you take this 1, 2. So these two are very closely. They should be touched with it. The nearest atom. So coordination number for this linear arrangement is 2. Okay, only 2 spheres are closely attached with one sphere. Okay, 2. Then 2D arrangement. 3-dimensional arrangement. In a 3-dimensional arrangement, you will have 2 types of arrangement. One is a AA type arrangement. Another one is a AB type arrangement. What are the 2 types of arrangement? AA arrangement. Another one is a AB arrangement. In AA arrangement is also called as square close packing, SCP. This is called a square close packing, whereas ABB is called a HCP. Hexagonal close packing. This is square close packing and hexagonal close packing. What is SCP or AA arrangement? See, this is linear arrangement. No, one by one, repeatedly the linear arrangements are repeatedly arranged in that. That is called a AA arrangement. For example, same way how first sphere is there like this. So there is no change, same like this you have to view. Next line, this is A type, again A type, one more A type. Likewise, this will go on like this. So all are arranged in the same way. There is A type arrangement. See, if you mark any one of this sphere, you take this sphere. Okay, any mark one of this sphere. How many spheres are closely attached to this? One. Here one. Here one. So now this sphere is attached with 4. So coordination number of SCP 4. Why is 4? We are differently writing like this. Okay, this one, this same one, downwards one. That's why it is called as a S is square SCP close packing. Okay. What is the coordination number? Coordination number 4 because this sphere directly attached with 4 other in number. Then we can see the A. This is called the AA type. Then AB type. AB type. If we go with the AB type, that is also a linear arrangement, repeated linear arrangement, but in a different way. Okay. See, in the second, the A type linear, the repeatedly linear arrangement, but you start with here, in between these two, in between these two, in between these two, in between these two. In between these two, in between these two, you go like this. Okay, then this is B type arrangement. Again A, like first, third layer should be like a first layer, first line. 1. So likewise, then this is A again A. Again B type, that is why AB type. Again you start with here. If we go on like A, B, it will go on like this. If you now locate one atom, one sphere, I am considering this sphere. See, how many of them are directly attached? If we go ahead, like this. Okay, see 1, 2, 3, 4, 5, 6 other. Now if you arrange this 1, 2, 3, 4, 5, 6. So here the coordination number for a HCP coordination number 6. HCP coordination number 6. Now this 6, let me draw again separately. Above layer 2, this is our particular layer. This side will be 1, this side will be 1, again 2 layers are there. So this is our targeted layer, sphere. And we see this 2, so 1, 2, 3, 4, directly attached, 5, 6. So this is hexagonal like, so this is called a hexagonal close packing, HCP. This is called as a hexagonal close packing, HCP. You have a coordination number 6, whereas SCP, AA arrangement SCP, you will have a coordination number 4. Here, hexagonal close packing, you have a coordination number 6. Okay. Comparatively to this, which arrangement is more stable? As you know very well, if we are with the union, we have a lot of friends, a lot of family members with us, we are very stable, we are energetic, isn't it? Likewise, here also, the coordination number increases, the stability is more increases, or more stable arrangement. If you ask among the SCP and HCP or AA arrangement, AB arrangement, which is more stable, which is stability is high, like that they asked, what do you say? The HCP arrangement is more stable because it is a coordination number 6, or otherwise it is closely or nearly attached with the 6 other numbers, whereas in a cubic closed pairing only 4, whereas in a linear arrangement only 2. So list of linear arrangement in only coordination number only two numbers are closely neighbor, whereas in a 2D arrangement, two types of possibility. One is a AA type, that is a SCP. Another one is a AB type, that is HCP. The coordination number of SCP, that is 4, whereas the coordination number of HCP, it is 6. Okay. That's why it is a more stable. HCP is a more stable arrangement. Then what about the 3D arrangement? 3D arrangement we can see in a separate class, next class, detail about the 3D arrangement. 3D arrangement is nothing but this is one layer, no? Above this one layer, see, this is a layer. One layer is there, first layer. You have next layer above this. Then you will have a 3-dimensional arrangement. There is a void, is there, everything is there, we see in the next class. Now let us move on to the packing fraction. Let us see the packing fraction. What is called packing fraction? As you see the cubical arrangement, if we have all atoms there is a empty spaces. See, as I said, the box can contain 20 balls, if you imagine that. Okay. If we put all 20 balls inside the box, after that, you can say the box is completely filled with the balls. Okay, you can say, sir, box is filled, all 20 balls are there. 20 balls may be inside the box, but there is a empty space behind it, inside the box. Likewise, if we are saying that packing arranged like this, there may be empty spaces. What is if all the volume of the box is filled by balls? No. But we cannot fill any one more ball? No chance. But you cannot say that is all the complete entire area of the box is filled by the balls. No. Likewise, if packing atoms or molecules are packed like this, you can see the empty spaces. So we need to the position packing fraction. Okay. How much total amount of volume occupied by the sphere divided by the volume of the unit cell. Okay, that is a packing fraction. You can write packing fraction is nothing but a total volume occupied by the sphere divided by volume of unit cell. Volume of unit cell. Okay, that is a packing fraction. For a simple cubic arrangement, today we are going to see the packing fraction. For a simple cubic arrangement, today we are going to see the packing fraction of simple cubic arrangement. For simple cubic arrangement, that we are going to see the packing arrangement. Total volume occupied by the sphere. Okay, then volume of the unit cell. Volume of the unit cell you know very well, that is A cube. Volume of the unit cell, that is A cube. Okay. Then total volume occupied the sphere. For simple cubic, edge length A equal to 2r. For simple cubic, edge length A equal to 2r. Then what is the radius? Radius r equal to A by 2. For a simple cubic, A by 2. Then what is the volume of the sphere? Volume of the volume of the sphere, that is equal to 4 by 3 by r cube. Volume of the sphere is nothing but a 4 by 3 by r cube. You substitute the r value here, 4 by 3 by into r equal to a by 2. Okay. Then 4 by 3 a cube by 8. Okay. Then 2. So by a cube by 6. That is the volume of the sphere. Okay. Then total volume occupied the sphere. Total volume occupied the sphere. Total number of atoms present in a sphere. So total number of atoms n. That is total number of atoms present in that z, we can say. That is z value for a simple cubic 1. So total volume occupied the sphere equal to by 3 by 6. Okay. Then what is the packing fraction? Packing fraction, that is nothing but a total volume divided by a cube. So packing fraction, efficiency or packing fraction of simple cubic, that is equal to by 3 by 6 into divided by a cube, that is equal to 5 by 6. So packing efficiency of a simple cubic is a 5 by 6. If we substitute this value, so efficiency means it into 100. So into 100. A percentage efficiency we want to know 200. That is equal to 9. If we substitute the value of the pi equal to 314 by 6 into 100. That is equal by 6. That is equal to 5. P2. So packing efficiency of simple cubic is 52.21%. What it means that in a simple cubic, atoms or ions are filled there. So totally, the entire volume, the total volume will be occupied only 52.21%. 52.21% only is occupied. What is the empty space? These are the empty space behind it, inside it. So the question may be asked, the space occupied in a simple cubic, the question is asked no. So what is the answer? 52.21%. So empty space, we have to be very keen about this. Empty space occupied in a simple cubic means 100 minus 52.21. What will be 100 minus 52.1? That is an empty space. So we have to be very keen about the question whether they are asking packing efficiency or the space occupied in a AC simple cubic or empty space. Empty space means 100 minus 52.1% will be the answer. Okay. Once again, packing fraction is nothing but a total volume occupied by the sphere divided by the volume of unit cell. The explanation you must know that you container you box up I assume that box is full of space, then balls you assume that. If you have maybe 20 balls may contain that container, the box. So after putting 20 balls, the container is filled. Okay. Now you can see the container is filled, but actually all the space of the container is not filled. Okay. Because when you arranging the ball in a different arrangement, there must be empty spaces, vacant spaces are there. So after we cannot say 20 balls is occupied. So this is volume of the container 20 balls. The volume of 20 balls equal to volume of the container. You cannot say. The volume of container is to something that volume of the sphere, that balls will be something. So the correct efficiency if you want to calculate, you should go total volume of occupied sphere. The ball may be sphere. Here in a crystal we can consider all the sphere in a unit cell. Total volume occupied by the sphere that you have to calculate. Then volume of the unit cell. If you want our percentage wise, into 100. You have to put into 100. Then the total volume of the sphere we can calculate. The volume of the sphere formula is 4 by 3 by r cube. What is the simple cubic? A is a edge length equal to 2r. Okay, in a simple cubic, A equal to 2r. So what is the radius? Radius equal to A by 2. So instead of the radius, we have to substitute the A by 2. 4 by 3 by r cube. Instead of the r, we are substituting A by 2 here. When you apply this, 4 by 3 by r, A3 by A cube by 8. If you cancel, you may get a by 3 and by 6. In a simple cubic, total number of atoms Z equal to 1. Okay, this is for a one sphere. But total number of sphere atom in a simple cubic 1. So it is into 1. Same value will come. So by A cube by 6. This is a total volume occupied the sphere. So what is the packing fraction? Packing fraction is nothing but a total volume occupied in the sphere divided by the volume of the unit cell. The volume of the unit cell is nothing but a cube. So you combine these two, the packing efficiency or packing fraction or packing efficiency both are same. By A cube by 6 into 100 divided by A cube. A cube will go there, A cube will be cancelled. So total packing efficiency or percentage efficiency, that is equal to pi by 6 into 100. You know very well, pi equal to 3.14. When you apply this value, you may get a 52.21%. So what is the conclusion is that in a simple cubic arrangement, out of the total volume, 52.21% of the volume is occupied by the sphere. So totally empty space, remaining thing, only 52.21% only occupied by the sphere, remaining are empty, total empty space. The question may be asked in one word, what is the empty space left over in a simple cubic, or what is the space occupied the sphere in a simple cubic? If they ask empty space 100 minus 52.1, you apply, you will get the answer. See, why efficiency is 100%, never you got 100%. Okay, will less. If more efficient packing, more stable. As you see that FCC will have a more efficiency comparatively, because we will calculate in the next classes of packing fraction of BCC and the FCC. Then you will find it is a leastly factor, 52. So number of packing efficiency it's giving the force of attraction. So it is very leastly packed, 50% only, almost 50% only is packed. So it is have the attraction between the spheres are less comparatively other type of packing. So 52. Number of efficiency increases, the force of attraction also increases. Here only 50% is occupied. So it is a leastly, the force of attraction will be very less in a simple cubic. Okay, this is a packing fraction or packing efficiency. Once again, let me explain what is packing fraction or efficiency. Packing efficiency is nothing but a entire total volume, how much volume is be occupied by the sphere. That is called a packing efficiency. So the formula may be right, total volume occupied by the sphere divided by volume of the unit cell into 100. Then volume of the sphere 4 by 3 pi r cube. For what system? It is a simple cubic arrangement we are seeing. So simple cubic arrangement, so the R value may vary for all. Okay, for simple cubic only A by 2 R value, because edge length A equal to 2R, then R equal to A by 2, then you are substituting the R value there, you are getting the entire, after applying all this, we are getting the value 52.21 as this. This is the space occupied in a simple cubic arrangement. Let us see the other cubic arrangement in next classes. Thank you.